Hello, my name is Jesus Valbuena. I am an international student from Colombia. I was assigned to the Restricted Boltzmann Machines group, and I chose to use the MINST dataset, which actually we saw a little bit about on the class last week when we were talking about the possible uses of deep learning algorithms. So I chose this dataset because it's actually recommended online as one of the datasets that is very useful to start with when one is playing with restricted Boltzmann machines. So this dataset consists of a set of numbers, and the point of the dataset is to be able to do digit recognition. So we have a bunch of columns that have pixels that are represented in them, and each column will have a pixel that is ranging from 0 to 285. And each of these values can vary from 255 to 0. So we have a bunch of numbers that we actually have to binarize. We have to normalize this data because the restricted Boltzmann machines have to work with binary data. In addition to this pixel information, we have a column that is going to actually give us the number that is represented in each row. So we have something like what we can see over here, which is going to be the representation of all the pixels actually. So each of these numbers is going to have a row, and we're going to have the first line in each row give us the number, the actual number represented by the pixels to the right. So basically there is some data preparation that needs to be done for the case study. That is not a lot because the data is already pretty much set for people to use. And it consists on normalizing the data that we have. So basically I had to divide every pixel number by 256 in order to have binary input for the restricted Boltzmann machine. So I either had a 0 or a 1 coming into the machine. And this was something that had to be done. So as I said before, this is a data set that is actually recommended to start using restricted Boltzmann machines. It turns out that deep learning models are what we have that is the most advanced at the moment for image and digit recognition. So this is perfect for this kind of data set. So we're going to use a restricted Boltzmann machine, which is actually a probabilistic model of binary vectors. There was a binarization process that allowed us to have either zeros or ones. So basically a 0 is there is nothing there, it's all white, and a 1 is we have some information, so it's something that could represent a number. And we're going to send the information, these binary vectors, from the visible layer to a hidden layer, which probably was explained by one of my classmates already, in order to get symmetric weights. And what we have to do is find the weight matrix and go back and forward between the hidden layer and the visible layer in order to get a prediction of the number that we're gonna end up having. So in addition to doing the restricted Boltzmann machine, I chose to get information on two more methods so that I could compare the accuracy of the restricted Boltzmann machines to something else. So basically there was another person who already did this online on a blog and explained the process pretty well using random forests on a blog called Beyond Balance. And I decided to run it through support vector machines like we did in class for case study number 2. And I will show you the results quickly so we can do a comparison. So basically the restricted Boltzmann machine, after going through the binary data, and which I was basically comparing sets of numbers, so basically I was giving it a set of zeros and ones and trying to see if you could guess if it was a 0 or a 1 that was represented in an image, or a 5 against a 6 or a 7 against a 1. I was able to get, on average, a 97% accuracy. The accuracy that you see on the slide is actually for the case of 5 versus 6. And then actually there is something that is really cool that we're able to do, is that we're able to reconstruct the number using the prediction. So this is actually the reconstruction that you see right here of the prediction that the restricted Boltzmann machine gave me. So like I said before, I ran other algorithms or went to look for the results of other algorithms, and I found someone who did this exact same experiment using random forests, and they were able to get an accuracy of 96.8%, which is pretty good, using bootstrapping and random forests that used 1,000 trees. And this was taken from the Beyond Balance blogspot, which is right here. And also I ran support vector machines using 4 different kernel types, so radial, polynomial, linear, and sigmoid. I was forced to use only sample sizes of 1,000 because my computer would crash if I did something that was a lot bigger than that. And I was able to get accuracies of, well, around 80%, like you see here. Actually, the radial kernel was closer to 90% with a value of 88. A polynomial kernel with 11%, which I'm not sure why it was so low, but I didn't look into it that much. Then linear kernel with 83 and a sigmoid kernel with 80. I tried doing some parameter tuning, but my computer crashed when I was doing that as well, so I stopped. Well, basically, I was able to get a much better result using the restricted Boltzmann machines, and I'm pretty sure with some parameter tuning this accuracy level can be even better, which I'm still looking into. I think it will be part of the final report. If you're interested, these are the R packages that we used that were actually explored by one of my teammates. And the MINST data set and the code that I used to load the data into R can be found right here. Thank you.